Hello everyone. This is a bonus example video for chapter 18. I want to do an example problem that involves working pretty much solely with the concept of pressure. And I will take one that was from chapter 14 in your book, and we'll do it together. And it gives us a chance to practice with the concept of pressure, specifically with water in this case, but in general, we'll be using the concept of the pressure of a fluid a lot in chapters 18 and 19. So this is for some extra practice. And the wording goes like this. We have a large glass wall of an aquarium, and it has length 5 meters. And, okay, sorry about that. We have a large glass wall of an aquarium. The wall has a length L of 5 meters and a height H of 3 meters, so it's quite large. And the aquarium is fully submerged in fresh water with its top at the surface of the water. In other words, the water completely fills it. And with air on the other side of the wall. The density of fresh water is rho equals 1,000 kilogram per meter cubed. Here's the question. Calculate the total force on the wall due to the pressure from the water. Okay, so to approach this problem, remember our systematic problem-solving method, the acronym STEMS. The first S stands for sketch. So let's start by drawing a sketch or two of what's going on. And I'll draw both a side view and a top view of this aquarium, just to make sure the situation is clear. From the side, there's the wall of the aquarium. You're seeing it from bottom to top. And there's the floor that it's bolted down to, right, like so. And then we have, of course, water on one side, all the way to the top and over to our left here, however far it goes that way. Turns out it doesn't matter, okay? All right, so that is the water side. And on the other side, we just have plain old air at atmospheric pressure on the right, as well as, of course, above. On the left side, right? There's air above the top of that water. Okay, that's my side view of the filled up aquarium. And if we just think about it from Physics 110 kind of thinking from last semester, there will be a force on that aquarium wall from the air on the right side, and that force will be inward this way. Okay, and I will call that F air. That's the force on our wall here due to the pressure from the air on the right-hand side. And there'll also be a force on this aquarium wall pointing to the right, like so, that will be due to the water as well as the air above it on the left-hand side. So I'll call this force from, I'll call it water plus air, because on the right I have air, okay? And on the left I have water, but there's air pressing down on top of that water from above. And that has an effect on the pressure. And clearly, it's pretty clear the force from the left is smaller than the force from the right because of the effect of that water. I want the net force on that wall from the water. In other words, it's a little bit tricky, but what the question is getting at is, what is the net of those two force vectors? The net, the total. And so that means just take the bigger one on the right from the water and the air and subtract off the one from the left from the air. And with the net left over will be just from the water. That's what it's getting at, okay? The wording there might take getting used to. Note, by the way, that my arrows there do not represent all of the forces on the wall of the aquarium. It can't be a free body diagram, which would have all the forces, because if that were the free body diagram for the wall of the aquarium, the net force would be to our right, and the aquarium wall would accelerate to our right. Yet we observe that the aquarium wall stays at rest, so the net force on the aquarium wall must be 0. But that doesn't matter for what this question is. This question just wants the net of those two forces. That'll be a net force to the right from just the effect of the water. Now let me also draw what I'll call a front view. Okay, so there again is the floor. And now, when I look at it from the front, this aquarium wall, like so, has all the water behind it as we look at it from the front. It's got a total length L, and it's got a total height H. And I'm going to draw a y-axis pointing down, let's say plus y is downward, with y equals 0 at the top, and y equals h at the bottom. I took the plus y-axis down. Why did I do that? Because the physics idea I'm going to need to solve this problem is how the pressure in a fluid varies with depth, specifically in this case water. How the pressure of a tank of water gets larger as you go deeper, which is going to happen here. And in chapter 14, which I talked about in the video lecture, and I referred to the sections in chapter 14, there is a discussion, there's a derivation of the formula for calculating the pressure in a fluid as you go down farther, variation in pressure with depth. And that formula is derived assuming plus y downward, and it's just easier in this problem to stick with that. Now, since the pressure does vary with depth, I'm going to have to imagine dividing up the area of this glass wall into little infinitesimal strips. I'll draw one of them, arbitrarily chosen. Okay? It's a little, very narrow rectangle of length L. In fact, it's so narrow, I'll call its width this way, dy. And its actual location, this way, is y. And y, of course, is anything between 0 and h. Okay, and so I'm going to start by getting a mathematical expression for the force from just the effect of the water on that little area shaded in red. And then we will add up all the forces on all the little rectangles that make up that picture to get the total. Okay, now, part of our problem-solving approach is to draw a sketch. That's the first S in STEMS. Then there's a T in STEMS. T stands for tabulate. What are we given? Okay, well, we know the length L of the glass wall, 5 meters. The height H, 3 meters. And we know the density, rho, of the fresh water used to fill this tank, 1,000 kilogram per meter cubed. So that's tabulating what we know. Then the E in STEMS is explain. Explain what physics idea you're going to use. Okay? And we're going to find what I'll call it the water force on the tiny strip that I've shaded there. Okay? It's got a length L, and it's got a width, not width, width, dy. All right, let me call that water force dF W. It's a tiny force due to just the water. Subtracts out the effect of the air. Okay? And we will just use the concept of pressure as force over area and mentally rearrange that. If pressure is force over area, then force is pressure times area. So to get the water force, I need the pressure just due to the water times the area of that strip. Okay? The pressure due to just the water, ignoring the extra effect of the air on top of the water, is called the gauge pressure, and it's a function of the y coordinate. And I multiply that by the area dA of that little strip. Okay, now I need to say some things about that. So, that notation, P sub G, is called the gauge pressure. You can think of that as the pressure excess above atmospheric. Okay? The pressure excess above atmospheric. And of course, the dA is the area of that tiny strip that I've drawn in red. Now, how do I think about this gauge pressure from the water? Well, here's what we know about calculating pressure with depth in a fluid. This is from Chapter 14. The so-called absolute pressure in the water as a function of y is equal to the pressure at the top. The book calls that P0, plus the effect of the weight of the water down to the depth y, and that ends up being the density of water, rho, times g times y. And since the top of our tank of water is air, and it would be at atmospheric pressure, the P0, the P at the top, is P atmospheric. So the pressure at height y, and this pressure is called absolute pressure, right here, just the actual pressure, all right, at that height y, is equal to the pressure at the top of the tank, which happens to be atmospheric, plus the effect of the weight of the water down to y, and that's the rho gy term. Now what I want, though, is so-called gauge pressure from the water, the excess above atmospheric. Well, just take this equation and subtract P atmospheric from both sides. So the absolute pressure at y minus atmospheric pressure equals rho gy. But the absolute pressure minus atmospheric is the excess pressure above atmospheric. That's exactly what we mean by the gauge pressure. So this is P sub g of y. And that's then just given by the simple expression rho times g times y. So with that in mind, I then have a nice simple formula for the force due to just the water on this one little narrow rectangular strip of the glass aquarium. It's simply rho times g times y, times the area dA of the strip, right? Rho gy is the gauge pressure times the area. But we already wrote down the formula for dA. So this is rho times g times y, and dA is, well, we talked about it, I guess. The length is L. It's just a rectangle, right? And the height or thickness is dy. So the area dA is L times dy. And we have a nice little symbolic expression for the water force on this one narrow rectangular strip. Now, to get the total water force on the whole wall of the aquarium, up like that, I've got to take the force on every one of the little narrow rectangular strips from top to bottom and add them up to get the total. And so I'm adding up an infinite number of infinitesimals. So we know what that means, right? So to get the net water force, I'll just call it FW, I'm going to add up all the DFWs. Imagine a whole bunch of rectangular strips from top to bottom and add them up. That's an integral. And so I substitute my expression for DFW, rho, G, Y, L, dy. So I'm integrating with respect to the variable y. So the limits on the integral are y values, and I start where y equals 0, that's at the top. And to get the whole glass wall, I have to go all the way to the bottom where y equals h. And that's the integral I have to do. And I've got several terms multiplied together and then a dy. So I can pull out front any multiplicative constants, any constants that are multiplied in here that are, well, they're constant. And that would be rho, the density of the water, is a constant. G is a constant. And L is a constant. So what's left inside the integral is y dy, with the limits going from 0 to h. That's a pretty standard integral. It doesn't matter if it's called y dy or x dx. It's still a pretty standard integral, right? The integral of y to the 1 is y to the 2 over 2. So y squared over 2, right? So this is rho g L, and then y squared over 2, and we got to put in the limits of our integral from 0 to h. And that's not too hard to do. When you put in those limits, you get rho g L h squared over 2. And that is our symbolic answer. Notice we have to do an integral in this problem to get the total water force, because the pressure from the water changes as you get deeper. It gets larger as you get deeper. It's not one constant pressure all the way down the wall of the tank. It's different as you go down. It gets bigger. And that's our symbolic answer in terms of things we were given, right? We were given rho and L and H, and we all know what G is. So it's just a matter here at the last step of now, after we've obtained the symbolic answer, and that's a big part of our STEMS approach. Then when we do the math, that's the M in STEMS, after we explain the physics, we strive whenever feasible to get a symbolic answer, expressed in terms of the symbols for the things that were given. And then, if the problem gave us numbers, we can plug in numbers to get a numeric answer for the desired quantity. So there's the density of fresh water, 1,000 kilogram per meter cubed. Of course, our old friend, little g, 9.8 gravitational field strength, Newton per kilogram. L, we were given 5 meters. H, we were given 3 meters. Don't forget to square that, H. All divided by 2. Okay, and if you look at the units, you've actually got a meter cubed upstairs and a meter cubed downstairs, a kilogram upstairs and a kilogram downstairs. The unit will be Newton. And you put those numbers in your calculator and you get 2.21 times 10 to the 5 newtons. 221,000 newtons is the net water force on this glass wall of this tank. 221,000. But the whole tank is in equilibrium at rest, so there must be a 221,000 Newton force to the left to balance that. It must be due to the fact that something is holding this wall down here firm. It's bolted down or something, right? With a waterproof seal at the bottom. But that's just interesting little detail. We have answered the question because we've calculated the total water force on the wall of the aquarium, and we see it is quite large. Okay? All right, so that's a bonus example using the concept of pressure in a liquid in this case. And that's all for this video.